Welcome back to Applied Mathematics. In this video, I'm going to be talking about some properties of triangles, many of which you're probably familiar with, some of which might be a little bit new to you. Let me get my head out of the way and we will dive right in. The first thing that I want to remind you of is that a triangle is formed by the intersection of three lines, pairwise. So we've got line AB, line AC, and line BC all intersecting each other. The other thing that I want to remind you of is that if you add the measures of the three angles in a triangle, you get 180 degrees. If you've ever been curious as to why that is the case, the answer may surprise you, but it's not that difficult to go through. If we draw a line through C, which is parallel to AB, well then we have two parallel lines cut by a transversal. And given two parallel lines cut by a transversal, alternate interior angles have the same measure. So angle 4 and angle 1 here have the same measure. I might even mark that by putting an arc in them to show that they're the same. But that's not the only transversal. These two parallel lines are also cut by this transversal. And that makes this and that alternate interior angles. All right, to show that it's different from the first one, maybe I'll put a double arc on those and say that the measure of angle 5 is equal to the measure of angle 2. And I'll abbreviate alternate interior angles. And really that's it. Because from here, I've got angles 4, 3, and 5. Together they form a straight line. And a straight line has a measure of 180 degrees. And then substituting, that means that the measure of angle 1 plus the measure of angle 3 plus the measure of angle 2 is also 180 degrees. 4 steps. And this is where things get to be kind of fun, because the parallel lines actually rely on some pretty key properties of geometry that aren't always true. When you are working on a flat plane, like the screen that I'm drawing on, or the screen that you're watching this on, or the paper where you're taking notes, well, it's easy to get parallel lines. That's a thing that happens. But if your surface is not flat, then parallel lines might not actually exist. So forgive my terrible drawing. But imagine the planet Earth. If you are at the North Pole and you walk in a straight line due south, following the prime meridian, you'll take a path that in perspective kind of looks curved, but you continued in a straight line for the entire surface of Earth. Having been going due south for quite some time, let's say that you now reach the equator. And once you have reached the equator, you're going to take a 90-degree turn and you're going to walk around the equator for a while. And I really do mean a while. You're going to walk a quarter of the way around the Earth. And then once you have made it a quarter of the way around the Earth on the equator, you're going to make another 90-degree turn, heading back due north to get back to where you started at the North Pole. And since you walked a quarter of the way around the Earth, if we look at that from a top-down view, it becomes very apparent that that top angle is a right angle as well. So if you try to draw a triangle on the surface of the Earth, you end up with a triangle that can have 3 right angles. That's 270 degrees, much more than 180 degrees. Or, living in southwestern Pennsylvania, working with land that is hills and valleys is kind of just part of life. And when you're working around hills and valleys, something that feels like a straight line can take some interesting twists and turns. And you can end up with a situation where maybe that angle is 1 degree, that angle is 5 degrees, and that angle is 20 degrees. 26 degrees. That is far shy of 180. This is one that has very practical application. I was trying to lay out a triangular garden plot for my wife, and I couldn't get it to connect to itself because the topography of my yard just prevented it. And so, yeah, I have basically that. A 1 degree angle, a 5 degree angle, and a 20 degree angle, which together form what looks like a nice triangle when you're not staring at it up close. All right, so the angles of a triangle can be a little bit weird, they can be a little bit unexpected, but as long as we're working on a flat surface, we can rely on the fact that the angles can add up to 180 degrees. We say that 2 triangles are similar if all 3 pairs of angles between them have equal measure. So if I draw triangle A, B, C here, and then I draw triangle X, Y, Z over here, if I know that angle A and angle X have equal measure, and I know that angles B and Y have equal measure, well, I know that the 3 angles of a triangle have to add up to 180 degrees. And if A and B are known, just subtract those from 180 degrees, and that's the measure of angle C. If X and Y are known, subtract those from 180 degrees, and that's the measure of angle Z. But since A and B and X and Y are the same measure, then it must work out that angle C and angle Z have equal measure as well. Right? That didn't have to be given to us. The blue pairs are given to us. The red pair is not given to us, but can be deduced. And that's all it takes to say that the triangles are similar. To denote that triangles are similar, first of all, we write out the name of the triangle. Literally, we draw a triangle and then write out the letters A, B, and C. Similar to is a tilde, a squiggly line. And then the place where we have to be careful of is when we name the second triangle, we have to make sure that the angles are named in the same order. I named angle A first. Angle A matches with angle X. I named angle B second. B matches with Y. And then the last angle C matches with Z. I have to make sure that those are in the same order, otherwise my claim is not true. And now that I have this, if two triangles are similar, the reason that that is a useful thing to notice, then the lengths of corresponding sides are in proportion. So if we consider this figure, let's go ahead and name the corners A, B, C, D, and E. And we know a couple of measurements. Let's say that we know that AD is parallel to CE. Let's say that we know that the length of AD is 3.25 meters. The length of AB is 3.50 meters, and the length of BC is, that looks like that's going to be something like 7.80 meters, and let's put BD as well. BD is going to be 2.95 meters. All right, so we have the lengths of a couple of segments in this shape. I don't know why I always enjoy drawing my triangles in a shape like that, but it seems to be something that I kind of default to when I'm talking about similar triangles. And my goal in this exercise is to figure out the length of CE. In order to get here, based on what we were just talking about, it shouldn't be too much of a surprise that the answer is to work with similar triangles. So before I start cluttering up the diagram by putting those length measurements on it, let's start thinking about what we know. I have two parallel lines here. Those two parallel lines are cut by a transversal, which means that alternate interior angles have the same measure. Angles C and D must have the same measure. I also know that these two angles at B have to be equal to each other because those are vertical angles. I'm lazy, I'm not going to write out, I should write out the names. I should not be lazy. So it's going to be angle ABD and angle CBE. And that's really all I need. I could make an argument with vertical angles again to get angles to get angles A and E matched up, but that's all I really need because I can now say that triangle ABD is similar to, and again, this is where I have to take the time to be careful. Angle A matches with angle E. Angle B matches with the other angle at B, and angle D matches with angle C. I have to make sure that I take the time to name the similar triangles in the correct order. And that is going to be incredibly important because the next step relies on it. I now want to set up my proportion so that I can solve the triangle. I can find that missing piece of information. So I will start with that missing piece of information. CE is going to be the numerator of the first fraction in my proportion. And let's see, looking through this list, we are given AD, AB, BC, and BD. I'm not putting the numbers just so I don't clutter things up, but I wanted to mark and remind myself of what I know and what I don't know. All right, so CE is what I'm looking for. I notice that the triangle that has CE, the only other thing I know is BC. So that's going to be the other part of that fraction. Now I have to figure out what corresponds. And sometimes this is very straightforward, just looking at the picture. And sometimes the picture is twisted in such a way that it makes it difficult. But if you took the time to write out your similar triangle name correctly, it's an easy match. I want to match CE. That's the first and last letter. So I come over here and I look at the first and last letter. Those are A and D. That's how I match it up. I need to match BC. That's the last two letters. I come over here and I look at the last two letters. Those are B and a D. That's it. I probably shouldn't have scrolled down because I need to actually fill in those values. I don't know what CE is. At this point, I'm going to go ahead and call it X because I'm much more accustomed to solving for X than anything else. But I know that BC is 7.80. I know that AD is 3.25. And I know that BD is 2.95. All of my units are in meters, which makes life easy. They don't all have to match up, but the more things match up, the less you have to worry about it when you go in here to solve the proportion. All right, cross product test, 2.95 times X, and then 3.25 times 7.80. My calculator tells me is 25.4. And then I get X by itself by dividing by that, and it comes out at 8.59. I typoed that. It comes out at 8.61. The difference between 8.59 and 8.61 is negligible as far as I'm concerned. So if you got that, that close, that's good enough. All right, moving along. Up next is the Pythagorean Theorem. I love talking about the Pythagorean Theorem because it's an excuse for me to talk about Pythagoras of Samos, the cult leader who the theorem is named after. Yes, you heard me right. Pythagoras of Samos does not count as a mathematician. He was a cult leader. His cult was in worship of ratios. He did a lot of work. Well, he didn't do the work. His followers did the work, and he took credit for it, of things like how to tune musical instruments by using similar ratios of string lengths. But one of the things that his followers were known for was working in geometry. So they discovered that if you have a right triangle, that is a triangle that has a 90-degree angle in it, the two legs of the triangle, which we generally denote as A and B, the legs are the sides of the triangle that are touching the right angle. But the squares of the legs added together gives you the same thing as the hypotenuse, the side that is furthest away from the right angle, also being squared. See, the problem with this theorem, and I guess before I get into anything else, when I say square, at the time of Pythagoras of Samos, that literally meant take this edge and form a square out of it and calculate the area of that square. By doing that, and going down just a little bit of logic, you can verify to yourself that the square root of 2 must be an irrational number, because you can't form a perfect square and then double it and still get a perfect square. That bothered Pythagoras, because irrational means it cannot be expressed as a ratio, and his entire seat of power is based around this cult where he worshipped and adored ratios and looked at ratios as the ultimate answer to the questions of life, the universe, and everything. So Pythagoras had the guy who came up with this killed. As you might imagine, townfolk who are otherwise accommodating of a cult because it brings population in and brings economy to the town will change their tune when someone is killing off their followers. So this is where one of Pythagoras's other quirks came in. Pythagoras, the cult of Pythagoreans, had a number of very strict rules unrelated to the study of ratios. One of which was that the cult members were not allowed to eat beans, because beans were considered to be the source of all evil and wrong in the world. And that was a problem, because with the townsfolk coming after Pythagoras, he has enough connections that he learns that they're coming and he gets a head start. But between Pythagoras and certain freedom was a farm. And on this field, they were growing beans. And so, roughly translated, as Pythagoras turned his back to the evil field of beans and bravely faced the torches and pitchforks coming after him, loosely translated, his last words were, It is better to die by the sword than to tread among the beans. All right. Fun out of the way, let's use the Pythagorean theorem. Again, the important thing about the Pythagorean theorem is recognizing that you have a right triangle. There must be a right angle marked. If there is no right angle marked, it is not a right triangle, and you cannot use the Pythagorean theorem. But here we have a right angle marked. We have two sides known in the triangle and a third side which is unknown. The reason that it is vital that you have a right angle marked is because you need the right angle in order to identify the hypotenuse. The hypotenuse is the side that is not touching the right angle. We call that C. The other sides are A and B. It doesn't matter which one is which, but when one of them is unknown, I almost always use A because it makes me happy. Now it's just a matter of plugging in. I don't know what A is. I do know that B is 2.750 inches, and I do know that C is 3.125 inches. My calculator is happy to do the remaining work. 2.750 squared comes out at 7.563, rounding to 4 significant digits. And 3.125 squared comes out at 9.766, again rounding to 3 significant digits. All right, so now we have the value of a squared, but we don't want a squared, we want a. So I have to take the square root. And here I want to talk a lot about the square root property. See, the problem with squaring is that when you square a positive number, the result comes out positive. When you square a negative number, the result also comes out positive. So, it's not clear whether A was positive or negative when I squared it to get positive 2.203. That's where I have to return to the logic of the problem, and I'm talking about the sides of a triangle. You can't build a triangle that has a side with a negative length. If you think you can, I'll accompany you to a workshop. I'll watch you build it, and I will help you secure a $1 million prize. I just asked for a 10% finder's fee. But for that reason, I know that A is positive. I don't have to worry about the fact that A could be negative. That is something particular to this application. I don't want you to come back and tell me if you continue onward to study of mathematics elsewhere, or even just the next course in the sequence, but you said we don't have to worry about that. That's because the application is geometry and negative side lengths of geometric shapes are nonsense. There are other applications where negative numbers are perfectly reasonable. All right, but we want the square root of 2.203. My calculator is quite happy to tell me that that comes out as 1.484, and since everything is in inches, I know that that's also going to be in inches. All right. There was a lot of ground to cover in this lesson. I hope that most of it was review for you. A lot of it should be things that you've seen at some point in the past. A couple of tangents I hope that were interesting. But I've gone on long enough, so I'll wrap up the video with that. As always, thank you for joining me, and I'll see you in the next one.